Hello and welcome back to another episode of Effective JaRu, the series where we read effective Java and try to apply the paradigms presented here to idiomatic Rust, which might mean that the paradigm doesn't apply at all. So before we get to the next chapter, which is chapter 3, I just want to finish up the last one because I kind of missed that in the last session. Presenting some finalizer tricks here. So what I learned from this passage is basically that finalizers certainly are non-deterministically called. You can't rely on them. You shouldn't rely on them. Also, if you are a subclass, then you have to, in a finalizer, you will have to call your superclass's finalizer explicitly, which is totally different from C++, for instance, where this call happens automatically for you. The compiler basically inserts this call for you. So that's really interesting to remind yourself of. If you want to protect against this kind of basically programmer error, it's another huge source for errors, if you ask me, then you can have a guardian object, which has no other purpose but to invoke its destructor automatically when the object goes or is collected, basically. And it's quite interesting that you have to use such tricks to assure your destructor gets called automatically. No, it's not a destructor, it's a finalizer, which is semantically different. So that's pretty bad. In Rust, obviously, we've clarified that there's drop. Drop is deterministically called at the end of the scope or at the end of the function at last. And that is it. You can use it. Actually, you should use it if you have to assure resources are cleaned up. So, chapter 3. That's a very interesting one. Obey the general contract when overriding equals. So generally, for instance, if you have a point class here, then a point, even though you don't explicitly state that, a point implicitly extends object. And if you do that, then you inherit certain standard methods, which are equals, hashCode, toString, clone, and finalize. Okay, finalize has kind of been handled last time, but the others haven't. And now it gets interesting, because the default implementations that you inherit regarding equals and hashCode will not actually work for your object. Because it's basically based on the identity of the object, and that's it. Because the base level object can only compare basically memory addresses, and that's all. But it's nothing that you would want if you actually want to compare two objects to each other, or if you want to use these in collections. The thing I find totally interesting here that you have to know that obviously it's implicit. And the default implementation that you get is highly to be broken. So if you just say, I want to have a point here and drop this into some hash maps, then weird stuff will happen or unexpected things will happen just out of the box and without getting any compiler warning or compiler support there. It gets even more interesting when you start to basically get your architecture a bit wrong. Generally, if you want to add a member to something by the means of extending that something, so if you want to have a colored point that extends point and adds another field to it, which is the color, then you're basically bound to break your equals implementation so that certain aspects of it are not working anymore. So it's actually the same thing in Rust, but Rust, I think, nails it. So what happens here? Where is it? Yeah, here is the list of things that need to be that need to be present or adhere to when implementing equals. Must be reflexive, symmetric, transitive, and consistent, of course. And there have been, he provides a few examples that show how these principles have been violated. And especially in the case of extending a class and adding a field, then you will always violate the equals relationship. If you are mixing equality comparisons between the subclass and the superclass, right? So as long as you stay or you compare only to color points, you're good. But if you start bringing standard points into the mix, you will be doomed. There's no way you get this right. This is nicely explained in the book. And the only way you get this right if you change your architecture to a composition model. So you have a color, you have a point, and a color point is then basically just a structure, or in this case, a class with two fields, a point and a color. And then you're fine. But this would also mean that you never really try to compare basically superclasses, right? Because you have none. I mean, this is the way to work around this. You don't imply that subtypes or subclasses and superclasses can be freely mixed and will work correctly in certain contexts where equals matters or where the hash code matters. So it's quite interesting. How does that pan out in Rust, you might ask? And well, this is basically the first module here. Item 8, I just created it for fun to kind of separate these different things, because we also have a case insensitive string here that shows a bit more about equality comparison. So in Rust, what we do is we just specify a point, we specify color enumeration, have a composite structure here, and in order to get equality right, all we have to do is tell the compiler to implement this for us. So partial equality is something we have full equality. Full equality is something that floats, for instance, can't do because of the not a number cases where equality can't be, equality is not consistent anymore, basically. So it violates some principles there. So for that, partial equality is required, right? But we can offer all or the best possible equality because we only consist of int and an enum here. So here's our structure, or our composite structure, that basically is a color point by combining a point with a color. And in the moment we want to use it here, you see that it just works out of the box. So principles work. We can use it in a hash set, which basically says, okay, 1 is equal to 3, and we can add 1, we can add 2, and in the moment we insert 3, we get a false here because nothing new was inserted. Equality basically prevented this from happening. Also, hash is implemented. And it would be interesting to see actually what kind of code the compiler inserts here. And there is a way to do this. If you do cargo rust C, we are able to basically just build but add our own options. So with Z unstable options, we get pretty printing. And pretty printing in this case will yield a nice pretty file like that, and then you see what the compiler inserts in a pretty printed fashion. So it's kind of full of stuff that you wouldn't write that way manually, but that's at the end of the day totally valid Rust, and it can look like that. So in order to get a hash here, you see that all it does is, well, it's a bit, you wouldn't probably write that in reality, but it basically extracts the field of the structure and then calls hash on them explicitly, right? And this arg0 is a hasher here that implements hashing for primitive types. So basically just does the full and correct implementation for you. And when it comes to partial equality, how does this look like? It matches on the other point, extracts fields, then it matches on these on yourself, extracts the fields, and then it compares. I wonder why it does this. This seems to be something that gets optimized away anyway. And yeah, I don't know why that is happening. It has no negative effect, but also it's kind of useless, I think. I don't know why you would do that, but probably there is a totally acceptable reason. Yeah, and this is that. Look at this. So that's how hashing works for an enumeration. It just assigns usizes to each item here and maps them. So if it's red, then you throw in a 0 here. Otherwise. That's how that works. The cool thing is that in Rust, hashing works using a hasher. So you in fact are, a hash type which implements the hashing algorithm. So you are basically independent of the actual algorithm used, or you can switch them around. Whereas here, the algorithm used is not decoupled from the implementation, right? So here we return an actual hash code, which is just an int, 32 bits. Let's see, I think in Rust, it's 64-bit. At least a hashable type where the hasher is the important one. So the actual hash returned here is a U64. So you have better hashes, the potential for better hashes in Rust out of the box. You can apply different algorithms which would help you to get, for instance, higher quality hashing functions if you like, which might be slower, but that might just be the right thing for you. Whereas in Java, you would have to implement the implementations of the types, which you actually can only do if you own the type, right? And that's quite interesting. This also means that you can't fake it here in Rust. You can't just return 42. You can't return weak stuff because you have to boil everything down to the primitive types, right? And otherwise or strings or byte arrays. So that's really, really interesting. And I prefer the Rust way, totally so. So what else is there? What is this? Assert receiver is total equality? Is this some sort of, it's a, oh, sure, that's equality for a color, but what's this assertion used for? That is interesting. I don't know. Is that part of the equality implementation? I think it is. I think it's part of the equality trait, huh? Assert receiver. No. Okay. That's also unexpected. Okay. But anyway, as you can see, it's all implemented for us, and it's correctly implemented. It's very powerful. It's nice, and that's something I clearly prefer. Also, it's not so wordy as the Java version is, but that's, I think, a common point or common possible criticism for anything that is Java. And yeah, some other example here where I think symmetry is broken. Is it symmetry? Yeah, here. Where symmetry is broken is a case-insensitive string. And I think this is, that equality breaks is actually an indicator that your design is wrong. I'm sure that the author has chosen this example just to show it off in something that people might actually do in reality. But I think you should probably never represent a case-insensitive string that way, even though it's quite common, I think, in super object-oriented languages like C++, because it seems to make things easier. On the other hand, it's kind of broken by nature because case insensitivity of a UTF-8 string does actually only work for a certain subset of characters, which is usually ASCII. So how does that work in Rust? Well, in Rust, you wouldn't have a custom string type. No. But you can use the std ASCII extension trait, which will allow you to basically ignore strings in a case-insensitive fashion. But it only only makes the comparison on ASCII characters. So I don't know how it works internally, if it just ignores non-ASCII characters or compares them byte-wise instead. But basically, the cool thing is that this explicitly shows you what it actually does. Okay, it only compares them in a case insensitive and fashion and in an efficient way, but only on ASCII, you know, and it can't be more clear because it's in the method name, which is quite a nice thing to have. So that would be really the equivalent Rust code. You wouldn't have a type of that. You could have, but yeah, I don't think this would happen. The good thing is, even if you have a separate type for this, you can, of course, do that in Rust just by, if you're really inclined to do so, have a new struct, case insensitive string, that has an inner string of some sort. But then, you know, you have to make decisions here and say, well, this is a heap allocated string. The bytes are heap allocated. And, you know, that's something you might also want. You could now start to make it generic and all that just to have a custom implementation of this. But in the Rust world, you know, there will never be any coercion. You can't just compare everything with everything. So equality issues just because you are mixing supertypes and subtypes will never occur. So I think that's kind of my word about this topic here. And I also think that this concludes the item 8 of chapter 3. Thanks for watching and have a great day.